Ladyada.
Hey everybody, and welcome to my desk. Happy Sunday, everybody. Happy in Manhattan. It's Pride weekend. Although it's like all month, it's Pride month. So this week we're working on a lot of electronics, e-ink displays and stuff. Any updates from you, Mr. Ladyada?
Yeah, this is for the fans that ride or die with not only Adafruit and Ladyada, PT, but this giant thing we're calling an art project, but it's really just our attempt to put a dent in the universe, to put more knowledge out there involving open source software and open source hardware. And this week, here's what you can expect ahead, because we have a full week of childcare. That means we get to do a lot more than we usually do. So during the week, you're going to see videos from us. We got show and tell coming up. We got Ask an Engineer. We have Rapid Render. We have 3D Hangouts. We have JP's product pick of the week. We have JP's workshop. We have deep dive. And then there's also 3D Hangouts in addition to the Rapid Render on Wednesday. And then we have Desk of Ladyada. And then we have probably 5 or 6 top secret videos. And then depending on what happens this week, the world will see if my little note to Arduino before they ultimately get acquired, they're venture capital funded, worked. There's some things I wanted Arduino to do before maybe Arduino isn't Arduino anymore. Look it up on TechCrunch. They got 54 million, so they're going to get acquired. I have a request, but I'm not going to talk about it or anything until they have a chance to look at it. And then if they do it, great, it helps open source. If they don't, I'm done. I can leave it on my blog for my notes of the Arduino ARC story. Then, for the people who are interested in AI and more, we have a few articles coming where we show how we're doing stuff, not only with Claude, but how we're, as a company, telling Salesforce and Slack that we want to make sure that our settings on our workspace doesn't have AI. Our company is a little different. We want our team to communicate with one another, and we don't want to eavesdrop and monitor on them, and we don't want a conversation that Ladyada and I, we're married, by the way, in Slack, because we use it to barf out in front of the whole company. Like, we want to just know that's never going to happen.
Yeah.
And I want my team to know that's never going to happen. And I know companies say, "Oh, this is our property. You know, don't you can't do that anyways. Use something else. Use Signal if you want to talk to your." Well, no, we get to run a company the way we want, and our employees, they like this. And so we're going to do something I think very special that's going to help everyone who uses Slack to make sure your settings aren't eavesdropping on you. And that, Ladyada, is what's going on this week. What do you got going on?
All right, so let's go to, thank you for the update. Let's go to the computer. So this week I worked a lot on e-ink displays and breakouts and stuff. We carry a lot of e-ink products, and we've got from other companies too, like Pimoroni, but we have our own little breakout boards like this 1.54 inch square e-ink EPD display, a 2.13 inch monochrome, tricolor, 2.9 inch. We got a couple different sizes. We got the flexible displays. We've also got the MagTag, which has been out of stock for a really long time. And the reason it's been out of stock for a long time is because this product used a 2.9 inch grayscale 4 gray level display, and it got discontinued. I bought all the ones that were available. I got the Ada box out. I got some for the store, but then they were discontinued. And the replacement couldn't do grayscale. They're like, yeah, we don't make the old one, and the new one doesn't do grayscale. And so I kept looking around everywhere for like, okay, can I get one that does the same 4-layer grayscale? Because a lot of our projects actually used it. Like, it was not essential. Like, I could have done it without, but a lot of our example codes and demos took advantage of the fact that you could get, some gradients to do, like advanced dithering or image graphical display. And so I couldn't get that for a long time. And then this week I kind of just sat down and I found a new supplier of e-ink displays. And even though they said they couldn't do grayscale, I kind of just forced my way through and figured out a way to do it anyways. So let's go to the overhead and I'll show off.
Yeah, just a little bit of a reminder, everyone. This is our overhead that we're testing. It's sharper, but just know that it's not mounted on a really sturdy thing yet. So when Ladyada moves it around, it might bounce, but like not too bad, right?
Okay.
You can zoom in on that if you want, digitally or.
Yeah, I just want to know it's. You got to figure out which way.
Yeah, you know what I'll do is I'll put arrows on the future desk for it. Okay.
Yeah, because it's not the way the other one was.
Yeah. Well, that one we've had for 5 years. So. That's right.
Is it?
No, you want to go. You want to hit it so it's mirrored.
Well,
no, hit the mirror button.
The mirror button?
Yeah, there's a mirror button. There you go.
Okay.
You
Cool.
done. And then you want to move it over.
It is upside down, so that's fine because now it's at least right side up.
And you could turn the whole thing too if you want.
Well, I don't need this to be as high up.
Okay. All right. After this, we'll set it up so it's
Okay.
real time live, folks.
Yeah. All right. So so one of the things I have to kind of tuck over here. So this is the monochrome display, and this is a 2.13 inch. And the thing about these is that they have this thing called the waveform table. And as you see, like as it updates, it does this like flickering flash thing. And which is also kind of, actually, you know what feels interesting? It's like the one thing that this is not good at because it doesn't do fixed focus.
I thought it did.
No.
I thought we had fixed focus.
I'm pressing the fixed focus button and it lasts for a second and then it undoes.
Is it because of the? It's because of the e-ink screen.
Yeah, that's what I'm saying. It's like this is like the one thing that
it won't stop doing it because it flips.
It's because when it flickers, it
Interesting.
Yeah, it's interesting. Well, we're learning stuff. It's okay.
Yeah. By the way, this is how you do stuff. You just do it.
You just do it.
Find out later. Okay, cool.
Okay, we're learning stuff. Okay, so this one, so you see it flickers, and as it flickers, it updates the display, and so that flickering effect is the voltages from the front and the back. Inverting back and forth, and that's what pulls the conductive ink particles forward or backwards. You can like read the Wikipedia about like how ink works. So these are little suspended particles, and you use like you can put a electric field across them, and it pulls the charged particles forward or backwards, and that's what makes them appear. And what's cool is because they're charged, and it's like with static charge, non-dynamic charge, you can remove power and the image stays, which is why they're so great for low power and daylight readable displays. There's also like partial refresh, which I don't really support, but there's a way to make it so it doesn't do the full flicker. It just kind of like refreshes just the page, but you do get a little bit of a ghosting. Whereas with this, what's nice is that it clears the display completely before it puts the new image on, so you get like a very crisp look. And you'll see that with like e-paper readers, like they'll often. You won't get a big flash when you update every page, but like every 5 pages, they'll do like a invert flash to clear out like any residual particles. So this is the monochrome display, and this is like the most common type. And then another type I got, so you see I could remove it, and it's like hi, the text is still there. So the other kind I got, which was kind of neat, is this quad color display. I have to upload new code, so give me a second. I'll compile and upload the quad color. And you can see just from this demo, it does, the 4 colors are white, the background, the black ink, and the red, which is pretty common. That's like, a lot of displays do black, white, and red. Red was kind of like, those are like really big particles. It takes a lot longer to update. And then there's also now yellow. Kind of like it's nice. And, if you have color images by doing like smart dithering, you can actually start, you're not going to get full color, but you're going to, with yellow and red, black and white, you can start to, get better graphical representation. Okay, so this upload? No, hold on. I don't think I actually clicked the upload button. And then the board, I'm using the RP2040 Think Ink, which is nice because it's a built-in. Almost every ink display uses the same connector. This is like a very, very standard 24-pin connector. So kind of the one nice thing about ink displays is that at least they kind of all came up with like, okay, we're going to use this. We use different chipsets and different firmware, but at least we use the same connector pinout and voltages. So this is quad color display. So you see it flickers a lot more, because every time you add another color, you have to do another kind of like waveform dance to get that color to appear. So the first color that they try to get in is the yellow, and then the red, and then black is last, because the black particles are the smallest ones. And you'll see like there's also like 7-color e-paper displays. There's one that are like full color, and those take a very, very long time to update because they have to flicker through this like extraordinarily complicated waveform with different delays and voltage levels to coax just the particles, because the particles are fully distributed. There's red, yellow, and black particles all over, but you only want them to pop in, in a certain spot. And so you have to kind of like get just those particles to pull up without getting the other ones too. And that's where you get these special waveforms. So, the waveforms are built into the one-time programmable memory on the chip. There's like a little, you can barely see it. It's like there's a little chip under this rubber gasket here. And that chip is what controls the display. Each one is slightly different. Unlike TFT displays, e-ink displays all have, for whatever reason, there is just like dozens of different chips. They all have kind of sort of similar, but totally different commands. And you can't get them slightly wrong. What is nice about TFT displays is, there's the HX57s and the ST778s and the ILI 93 for whatever, but they all kind of have the same command set. And so even if you have the wrong, if you get the wrong chipset, you'll get something. Like it might be inverted, or the colors might be wrong, or it might be like offset incorrectly, but you'll usually get like something to display, because the commands for display on and the commands for invert display and the commands for like draw pixel are all the same. They've all kind of come up with the same command set. That's not true for e-ink displays. They're similar, but they're not equivalent enough. And so you actually have to get like the exact right code. And if you have custom lookup tables, you have to get the exact right format, or it totally won't work. It's very opaque and undocumented. So what is interesting is go to the computer, is in the library, I've got drivers for the different popular chipsets. So the chipset I'm using for like the panels I just showed is the SSD 1681. And, I've got the register commands for what it does. And then there's this default init code. And the default init code actually, it doesn't have a lookup table, because it just says like use the built-in lookup table. And that's usually, like I said, monochrome or like quad color, whatever it's built in to be able to do. And then, there's some custom code for like, well, how do you do the update? The commands have to be, correct. And for powering up, you have to send it correctly. But when I actually define the panel itself, so there's the driver, the chip that drives the panel, but then the panel itself has its own specific, because it could be, you can have an SSD 1681 driving a tricolor or monochrome or other, like it can drive different kinds of chips, and you're going to need different lookup tables for each one. And so for each display, you might have different commands for, different initialization code for different like bring ups, like the different modes you want to bring up. So partial mode has a different mode. And for this one, the 2.13, which I'll attach in a second, I found a different display panel that said, oh, you can do grayscale mode. And they kind of like didn't document it, but they did have it in one of the examples in like this this commented out section. They had a lookup table, and they're like, oh, this lookup table will let you do grayscale. And so I ganked that, and this is the lookup table. So it's this 233 byte long waveform table, and you can look, in the data sheet for the SSD chip, they tell you like what each byte means, like the delay and the voltage and like how high it goes and how low and how long it waits and how many cycles. The only thing is, it's like you can't guess what the waveform has to be. Like the only people who know the waveform are the people who made the panel itself. Like there's no guessing, and you can like mess with it. But for stuff like grayscale, which is a hack, it's not like if you ask these panel makers, you say, hey, did you do grayscale mode? They'll say no. You kind of just have to like hope that you get something that works. So let's open up the grayscale example. Okay, so this is 2.13. Okay, so for this monochrome display, if you go to the overhead.
Overhead.
Let's hold on a second. For this one, like I said, it's not officially supported. It probably will reduce the lifetime a little bit, maybe, because you're doing a weird waveform. But again, I could not find any displays that were like natively advertised and supported as grayscale. I'm trying to think of an example. It's kind of like a weird hack. Like they kind of tell you not to update the lookup tables, but on the other hand, there's kind of nothing stopping you. And what's nice is that because now I've got a lookup table that seems to work for anything with an SSD 1681 or 1680 chipset, like these are the chipsets that are used, I think I'll be able to get the 2.9 inch version working well. So the first, for this example code, I first do monochrome just to verify. And this is, again, using the built-in lookup table. So it's very fast. You can see it's very crisp. It has the lines. And then what it does is it'll go into grayscale modes, that 4-layer grayscale. And you'll notice with the lookup table, now it's much slower. Like it does these much longer, like pull. Because the thing that's interesting, it's not a different particle. You're just pulling different amounts of particles. You can see here it's dark, light, dark, medium, light, and repeating. And then the next demo is going to show like a bar display. Maybe I'll unplug it so you can see it a little bit better. So yeah, this is the grayscale. So what's interesting about this grayscale mode is you see it's not like it's not true gray, right? Like it's not like there's a gray particle. What you see instead is like it's just not fully, it doesn't fully pull the black pixels all the way to the top. It kind of leaves them like halfway through it so that they float. And so it's a little bit granulated, but as long as you only really notice it when you have big chunks here. It doesn't look as good as the like official grayscale displays. Like I looked and those, you do get a much smoother, not significantly smoother, but it is a smoother look. But like I said, if I can't get something and I want to get the mag tag back in stock, this is kind of what I got. So the good news is that I'm going to get some of these monochrome 2.9 inch displays, but I should be able to run this code on them, and we'll update the driver for CircuitPython and Arduino, and then it, other than that, it should be drop-in compatible. It's the same pinout, and it's the same resolution. So the only thing that changes is the driver code. So we'll see. So that's coming up soon. How am I doing on time?
You're doing great. You have 18 minutes in, so
okay.
You have about 12 minutes or so out.
Okay. Oh, another thing, I'll just show this really, really fast. I did for a little for a kids project that we're going to have in the store next week. I did a little simple soil sensor. So this is a resistive type soil sensor, and it's going to be with gold, not silver or hassle. This is just hassle finish. This is a simple transistor version. And the interesting is I've always kind of not carried or designed anything with these. It just uses the resistance across these as the base resistor to, and then the beta of the transistor is what defines the voltage across, the emitter resistor. And these aren't great. They do oxidize because you have a differential voltage, across the two. Gold, of course, will help, but you're still going to eventually get some gunk on there. But, when we were talking to the educational group, they're like, well, price is really, really, really important. And I was like, well, it will be a couple dollars cheaper than if I had a microcontroller on there that did like full capacitive sensing. So, and this is, it has just a true analog output. It's quite simple. So despite this being not how I normally would design, sometimes cost dictates the design. Sometimes you just have to go with something that's going to be like a 1 cent transistor. Because
we do stuff with tariffs now. Like when your bill of materials has a little spot where it's like, will this cost 10 times as much by the time it gets here?
Yeah, you do have to think about it.
Very different.
And it's like, well, they really were like, no, the sensor has to be like,
it's like designing an
50
AR.
cents bomb. And I'm like, I can't do 50 cents bomb the minute you have a microcontroller.
I don't know how, there's probably a commercial company that's going to do this, but it's like you're designing virtual reality. It's like you pick up a rock. It's not a rock. There's like enormous amounts of bugs underneath it and like creepy crawlies that are going to charge you money. Surprise.
Yeah.
So,
Okay.
anyhow,
And that's it. Let's go to
that leads us right into what?
the great search.
Oh yeah.
Where in the world is that part I need? The Great Search with DigiKey.
The Great Search brought to you by DigiKey and Adafruit. Every single week, Ladyada uses her powers of engineering to help you, yes you, find the things that you are looking for on, I think, the world's biggest supplier of electronics and more.
Yeah, easily.
DigiKey.
Yeah.
Ladyada, what you looking for?
Okay, so we just talked about doing a bunch of e-ink stuff, getting some e-ink displays up and running. I'm gonna, it's like, I could tell these people like e-ink is one of the few things where, even before using AI assistants, like it's just like mind numbing. It's like very frustrating to work with e-paper displays because there's very little documentation. They don't work. There's like you kind of don't really know what you're doing. And eventually it does work, but it's like somehow you just lost like 5 hours. And so I'm kind of, this week I was like, well, like the weather's good and I have some extra childcare, so let's do e-ink stuff. And so I got a bunch of displays up and running. And I'd like to kind of expand to do more displays because I want to revisit the MagTag, but also want to make a bigger version using like maybe this like 4.2-inch e-ink display, like cool big display. So one thing that we do when we have breakout boards for e-paper displays is that if you have some e-ink like this is 400 by 300 pixels. So let's just bring this up. So this is 400 times 300 pixels times 2 colors per pixel, and then it's 8 bits per byte. So you need 30 kilobytes to buffer the display. And what's interesting about e-ink displays is unlike TFT displays, which almost always like the little, the little plug-in SPI displays. These plug-in displays 99% of the time have built-in video memory. You just tell it what window you want to write and you can draw within it. And so you don't have to buffer the full display. You just draw whatever pixels you want, which is great because otherwise you need like 500 kilobytes of video RAM. E-ink displays are different. E-ink displays do not have built-in memory. They write you write the RAM. The RAM is buffered to the outside of the display, and then you usually turn the display off until you lose that RAM. Like there's no like back RAM to reference. And so when you draw to these displays, you basically have to have the whole image ready to go, and then you blit the whole thing at once to display. And so in this case, for example, like we did the math, you need 30 kilobytes of RAM. Now, if you have like, an ESP32, an RP2030, or like, an IMX RT, 30 kilobytes is nothing. You're like, no problem, malloc it. You got it, you do it. But sometimes first off, there's a lot of people who are still using older microcontrollers, like at Megas, or maybe like smaller PICs, or, other small chips, maybe even ESP8266s, which will kind of, you can do 16K, but once you get 64K, they start to be like, I really need that RAM for doing Wi-Fi stuff. And so what we do is we often, on the breakout boards, have some RAM on top, some SRAM. Because e-ink displays are such slow to update. They take a really long time compared to TFTs, which are like nearly instantaneous, 60 frames, 30 frames a second. These are like easily a second, and the bigger displays, especially the color displays, you're talking about like 17, 20, 30 seconds to update the display. It doesn't really matter if you have your SRAM off chip where you keep your image buffer, because it's only going to add 200 milliseconds or whatever, maybe, to the display time. And it's worth it if you can, if the chip is inexpensive and you're using like an Arduino Uno, you don't want to update, this gives you access to drawing to those big displays. So let's look for SRAM chips, and we're going to look specifically for one that does SPI, because I2C is going to be a little too slow. Also, we already have SPI interface on the board because the e-ink display is SPI. So this is for active. And then there's non-volatile and volatile. So you're going to spend much more for non-volatile, which means it stays, it's like FRAM. It'll stay after you remove power, but we don't actually need that because we're just, we draw the buffer over every single time. Let's look only for surface mount chips so we can easily mount it. And then another thing we want to look for is the size. And so it's a little confusing because, let me see where the sizes are. Sorry. Clock frequency, memory organization. So there's memory size, and that's always done in kilobits. And then there's organization, which tells you, like, is it in 6? Sometimes it's 32 bits wide. We actually don't care. We're probably going to end up with 8 bits. But let's do the math on that, the memory size. Now, remember, I showed you one that was 400 by 300. But actually, if you're looking at the 7-color ASEP, like the very large, beautiful color displays, those are about 640 by 480-ish. So just the number of pixels is 300,000 pixels. And then you have 7-color, but those are packed, so it's 3 bits per. So each pixel has 3 bits, and then you divide by 8 to convert to bytes. So you basically need 128 kilobytes, but it's okay for it to be a little bit bigger. So let's only look at, and this is bits, and so it's 1 megabit almost. But let's look at, let's do by memory organization. It's a little easier to understand. So let's look at only times 8, because it's a little less confusing. We could do 64, but let's start with, let's just pick 64 just in case, there's some cases which we might want it. 128 by 8, 256K by 8, and 512K by 8. That's plenty. And let's apply. So now we're only going to look at the memory size, the sizes that make sense, because you're going to always pay more for bigger memory. And then we want SPI, so we'll get rid of the I²C. And then finally, there's some good options, but we want to, start to see there's a bunch of chips. We want to look for ones that can do the voltages we need. 2.2 volts is way too small. We're going to do 3.3 volt logic. So we just want to make sure that we select all the voltages that are within our range. Lastly, I don't want a BGA, so I'm just going to select all the ones that are not BGA, just get rid of the few that aren't. And there's NVSRAM, but again, I think that's going to be more expensive. We're just going to filter by cost. So let's put in, price at 250, and then we will sort by 250. And we got some good options. So the 23 series, this is a generic name. There's the 24 series for EEPROM, 25 series for SPI flash. 23 series is SPI SRAM. And you see these are 64K. We want, maybe we want a little bit bigger. So you're going to pay more. The cheaper ones are always going to be the 64. So let's start looking at 128. So this is 1 megabit, 128K. And looks like there's a couple options. This one is, the least expensive, but there's, a few. ISI has some, Microchip has some. Some of these are more or less expensive, I guess maybe depending on the volt. Some of them do only 3.6 volts, some of them go up to 5. Again, I have a level shifting on these boards, and I'm dealing with 3-volt logic. So I think I'm just going to go with this one. This one's fine. So it's 1 megabit SPI. You can do quad SPI if you want, but normal SPI is fine. And 1 megabit, this is plenty large, 128K. And then if I don't need that much memory, you save $1 by going to this one, 64 kilobytes, 512 kilobits. Same pinout. The good news, all of these are very code compatible. It's just how much memory you get to address. So one thing that's nice is on the breakout boards for our smaller displays, I use a 16K or 32K kilobyte RAM. And as I'm going to get to the bigger displays, I'll put a bigger RAM on to match that, the display resolution. So this is my pick for external SRAM. Could be very useful for you because, again, sometimes you can't add more RAM and you don't mind if it's slow. You don't have PSRAM support. SRAM is inexpensive and easily available.
It's a great search. Useful for you and useful for you. You can use the inflection different. It's a great search.
Where in the world is that part I need? The great search with DigiKey.
All right, we're gonna go eat, and we're gonna convert that food into brain cycles that make electronics and trouble. Bye, everybody.
Bye, everybody.